Leibnitz or alternative series test. If an is a monotone decreasing sequence of a positive terms and converges to 0, then sigma n varying from 1 to infinity minus 1 raised to power n minus 1 an is a convergent. Proof: here an is a monotone decreasing sequence of a positive terms converging to 0. So we have one an is greater than 0 for all values of n. Second, an is greater than equal to of an plus 1 for all values of n. And third, an tends to 0 as n tends to infinity. Let Sn be a sequence of a partial sums of sigma minus 1 raised to power n minus 1 an. So S2n equals to a1 minus a2 plus a3 minus a4 plus so on a2n minus a2n, which implies S2n is greater than equal to of 0 for all values of n. Equation 1, because the content of each bracket is greater than equal to of 0, again S2n equals to a1 minus a2 minus a3 plus a4 minus a5 plus so on plus a2n minus 1 plus a2n equals to a1 minus sum of the positive quantity which is less than a1. So S2n is less than a1 for all values of n. Equation 2, from 1 and 2 we get 0 is less than equal to of S2n is less than a1 for all values of n. So Sn is a bounded sequence. Also S2n minus S2n plus 2 minus S2n equals to a2n plus 1 minus a2n plus 2 greater than equal to 0. So S2n plus 2 is greater than S2n for all values of n, which implies S2n is a increasing sequence. Also S2n is a bounded above, so S2n is convergent. Let S2n tends to S as n tend to infinity. Now S2n plus 1 equals to S2n plus a2n plus 1, which employs limit S2n plus 1 equals to limit S2n plus limit a2n plus 1. So which employs limit S2n plus 1 equals to S plus 0, because n tends to 0 as n tends to infinity. So which implies limit S2n plus 1 equals to S. Now S2n tends to n S as n tends to infinity, and also S2n tends to S as n tends to infinity. So limit n tend to infinity as n tends to S. So the given series sigma n varying from 1 to infinity minus 1 raised to power n minus 1 into an converges to S.